When we last left my previous video, I was talking about the links between logic and programming, the wonderful relationship that is the Curry-Howard correspondence, where every logical proposition has a corresponding type, and every constructive proof corresponds to a computer program that implements that type. In this video, I'm going to cover the logical operations of and, or, as well as the predicate equals. I'll show how they have equivalences in type theory. I hope you'll be able to experience some of the wonder and joy that I felt when I learnt all of this. You might have encountered logical AND. It's the logical operator that is true if and only if both of its arguments are true. In classical logic, it has this truth table, and we can also represent AND with these rules of inference. From A and B, we can infer that A is true. We can also infer from A and B that B is true. If we have both A along with B, then we can infer that A and B is true. So, what is the type equivalent to this? Well, in natural language, we often use AND to create pairs of things, like TO and TR, spy and family, Holmes and Watson. If we have a type that is a pair of items of different types, would this work as our AND equivalent? Yes! If we have a type that is populated with pairs, with one item from the first type and the other side of the pair with an item of the second type, in order for it to be populated, we will need an item from both types to exist in order to create one of these pairs. Now, if any type involved is uninhabited, then it is impossible for this pair type to be inhabited because there is nothing to populate that item's slot in the structure. The only way a pair type can be populated is if we have items from both of the constituent types. There was a brilliant comment on the previous video from Mahai Nati that function types acted like exponentiation. Well, pairing in this way very much acts like multiplication, which leads to the name of product type. And this is why we are justified using the multiplication symbol to represent it. The three inference rules for AND also have three corresponding functions. The projection functions, PR1, which is A cross B to A, and the projection function PR2, which is A cross B to B. These projection functions allow you to extract a witness from the first or second elements of a pair. If you are familiar with functional programming, these are often called FIST and SINT. This inference law corresponds to the constructor pair, A to B to A cross B, which in most places, including Haskell, is just written as this, which I'm not going to attempt to pronounce. Well, now we have ANDs. How about that other key part of logic, the humble OR? ORs are true if at least one of the arguments to them are true. And OR is also true if both sides are true, as in this classical truth table. A few of you with backgrounds in classical logic, digital electrical engineering, or Minecraft Redstone might have already thought, we already have AND and NOT. Could we just make an OR out of them? Congratulations, because in classical logic, that's exactly what we would do. However, this doesn't work in constructivist logic. So let's dig a little bit more into computer science to find a working solution. Let's use an example of a rather common problem you'll often run into programming in the real world. Say you are writing some sort of weather statistical system, and your job is to write the program that downloads the temperature recordings from the sensors all over the country and store them. Another team will write the program that will do the processing of this stored information and make the results. However, you have a slight problem. Not all the temperature sensors are made by the same company, so they present the data in slightly different ways. Some of the sensors give the output as an integer, whole number values. The other sensors are made by a completely different company and output the values as floating points, so decimal values. These are represented differently inside computer memory, although in most cases they might take up about the same amount of space. At some point, you'll want to convert these values to be in the same form. However, the program that collects the raw values from the sensors might not be the program that does the conversion, and management has given you the requirement that the raw values have to be stored before any processing is done. They explain this because if there's a bug in the processing, they want to be able to go back and rerun the processing on the archival values. Well, we know about product types. Could we use one of them here? Well, we could make a type that looks like this, with a sensor ID, a temperature in float form, a temperature in integer form. That allows us to store both types of temperatures. Oh, and the field names are just there for readability. They're not really a part of the type itself. There is a problem though. While we're able to store both types of values, there's no way to know which value we should use. So let's add an extra format field for that. This format field contains a tag which tells us to use a float or an integer. Then we know which of the two fields to use. However, this is rather inefficient. There's always going to be a field that isn't used. If we were gathering a lot of data, that's a very large amount of wasted space. But in a computer, a float and an integer take up about the same amount of space in memory. It's just how the computer interprets these bits in memory that determines what they are. So if we had a way to tell the computer how to interpret the memory location, and if we had it treat the memory location differently depending on that, then that would give us a clean solution. And we already have this format field, so we could restructure it like this. In computing, types like this are often called tagged union types because they contain a union of two possible types and a tag to tell you what type to use. Other names for this kind of type are coproduct type, or the name that I will be using, sum types. And sum types will work perfectly well in our types and propositions world as well. In type theory, some types are notated like this, A plus B, and are populated with a tag and elements from either A or B. Some types are populated with as many elements as the elements in the left side plus the right side. Just like with product types, the inference laws have corresponding functions. In L, or in left, which is A to A plus B, in R, or in right, which is B to A plus B, and rec A plus B, which is this. I'll explain why this is called rec and what the pi is doing here in our next HotT video. But for now, I'll explain it as being you can create a witness for C from A plus B if you have a witness of A to C and a witness of B to C. I think this makes sense. You have to have a function to be able to handle each of the potential types that could be in our sum type. In functional programming language, this function is often called either. We have reached the point where we have a system of logic and propositions. However, at this moment, we don't have a way of getting information from the element level up into the proposition level. For that, we are going to need predicates, a way to ask questions about the quality of the entries that inhabit these types, and one of the most fundamental properties of an entity is equality. Are these two things equal? Is a pretty important question. It is the basic question that all of primary and much of secondary school education is constantly being asked of you. In type theory, everything that is a proposition, everything that we could have a yes answer to, is represented by a type. Equality is no different. When a type is defined, it also defines a whole family of equality types, one for every combination of two entities within that type. If the two entities are equal, then that type is inhabited by a witness. The simplest way two things can be equal is if they are the same entity. In this case, the equality type gets a witness called riffle, short for reflect. This is called judgmental or definitional equality. But two things can be equal without being exactly the same thing. Let's have an example. Say you want to represent the rational numbers, the numbers that can be expressed as a fraction. One of the ways you can do this is as pairs of whole numbers, a numerator and a denominator. And yes, I haven't defined how we're going to do whole numbers yet, but let's just assume that whole numbers just work the way you expect whole numbers to. We good with this? Excellent. Now, clearly, in the case of 1, 2, 1, 2, both numerators match and both denominators match. They are both equal to a half. So clearly, equal. But what about 2, 4? 2 quarters is also a half. If we want to have a system that works like rationals, we need some way to say that these two things are equal. This is done by adding to the type a uniqueness principle. A uniqueness principle basically allows multiple entities in a type to be different names for the same thingy. Technically, the proper name for this is a referent, but thingy works just as well. This uniqueness principle requires that any function that interacts with these entities as a domain to treat these entities exactly the same. So the function should always give it the same output if these entries are put in. This type of equality is called propositional equality. So for a rational type, we say rationals are equal when they're the same value, or a value that you get after multiplying the numerator and the denominator by some whole number, so long as the whole number has an absolute value of 1 or more. Why did I use such a roundabout way of saying non-zero? In constructivist logic, it is often easier to talk about positive statements rather than negative statements, just because of the way that we don't have the law of the excluded middle. With product types and sum types, we have the ability to combine propositions together so long as we are dealing with a fixed finite count of propositions. But in order to express things like the rational numbers uniqueness principle, we are going to have propositions that operate on an unknown, possibly infinite count of propositions. For that, we are going to need the tools which will be provided in the next video in this series, pi types and sigma types. So please subscribe to learn about them when the next video in this series comes out.